This is the Chapter 2 homework for Physics 102A. We'll start with number 13 on Chapter 2. It says a trip from Earth to the Moon, about 385,000 kilometers, takes 2.5 days. The average speed for the trip is what? So average speed is going to be the distance over the time. 385 times 10 to the 6 meters. Divided by 2.5 days. So the reason I did meters is because the multiple choice answers are all in meters per second. So we're going to want to put that in meters right away. And we need seconds. So a day is 86,400 seconds. And we get 1782 meters per second. Looking at the multiple choices, we can see 1800 meters per second is the closest one to that, but this is appropriate because we are allowed two significant figures because of the limitations of the two significant figures of the time, 2.5 days. Number 19. The average acceleration to boost a spacecraft from 1250 meters per second to 1870 meters per second in 35 seconds is what? And I'm going to start by saying V naught and V, and then the time. Average acceleration is change in velocity over the time increment. And I can see I actually did the units wrong here, so let me put in a meters per second squared. Okay, so change in velocity over time, and we end up with 17.7 meters per second squared. Number 31 says, how much time does light from the sun take to reach the Earth? Well, we're going to need for time, we're going to need distance and the speed. And so we look in the appendix and we see the distance between the sun and the Earth is 1.5 times 10 to the 11th meters. The speed of light is 3.00 times 10 to the 8th meters per second. That's from the top in the front flap of your textbook. And so average velocity or average speed is displacement over time. Solving algebraically for time, we then have time is the displacement over average speed. So we do the displacement, 1.5 times 10 to the 11th meters divided by this average speed. In this case, it's the speed because it doesn't change, but 3 times 10 to the 8th meters per second. So we get 500 seconds, or about 8 minutes and 20 seconds. For number 33, if you run 4 meters per second for 100 meters, then at 5 meters per second for another 100 meters, what is your average speed? And if you go to the bottom of the page here where my marker is, you can see average speed is displacement over time, how far you go divided by the time. And as we begin this problem, we're not quite ready with that information. We have to do some things to figure those out. So let's go to the top. Here I've drawn a simple diagram. There's the part A where we're running at the one speed, and then part B where we're running at the other speed. And for part A, we go 100 meters at a speed of 4 meters per second, but what we're going to need down at the bottom of the page is the time that took. So I'll call that T sub A. And then for part B, we have the distance, we have the speed at B, but what we really need is the time, and I'll call that TB. Well, the time for part A is distance over speed, dA over VA, and that becomes 25 seconds. The time for part B is that distance, 100 meters, divided by the speed, 5 meters per second, and it's 20 seconds. So the total time for this entire trip is 45 seconds. Now, if we want to know the average speed, that's displacement over time, 200 meters over that total of 45 seconds, and we get 4.4 meters per second. Number 39 says a dog sled goes straight at 9.5 meters per second for 10 hours. Then the dogs rest for the remainder of the day. What is the average velocity for the entire 24-hour day? Well, average velocity is going to be displacement over time. So let's first look at their displacement. displacement is speed times time. They went 9.5 meters per second times 10 hours. But we have to deal with this seconds versus hours. We need the consistent time unit. So let's convert that 10 hours to seconds. We're going to multiply it by 3,600 seconds per 1 hour. So when we multiply the 9.5 meters per second by the time of 36,000 seconds, we get 342,000 meters. That's the displacement. The time, we're going to need that in seconds. It's a day, but we're going to convert and say 86,400 seconds per day, so 86,400 seconds. Then we put it together. Now that we have displacement in meters and time in seconds, average velocity is displacement over time. I've plugged in the numbers and we get 3.96 meters per second. So that is the average velocity, which includes that most of the day they were resting. Number 53 says, the next three problems deal with a stock car which starts from rest at time t equals 0 with velocity in meters per second increasing for 4 seconds according to the function v sub x is 1.4 t squared plus 1.1 t. All right, so there it is, that given information. And question A for number 53 asks, find the car's velocity at the end of the 4-second interval. And then part B, find the average acceleration for this interval. Okay, so the velocity when time is 4 seconds, we're going to take 4 seconds, plug it into the equation given at the top. So 1.4 times 4 seconds squared plus 1.1 times 4 seconds. And we get that the velocity at the end of that interval is 26.8 meters per second. Question B asks, find the average acceleration for this interval. Average acceleration is change in velocity over time increment. Well, the change in velocity, it went from 0 to 26.8. So 26.8 minus 0 is that numerator, 26.8 meters per second. It did it in 4 seconds, so we divide those, and we get an average acceleration of 6.7 meters per second squared. Number 55, estimate the instantaneous acceleration at t equals 2.0 seconds. So what I'm going to do is look at what is the velocity immediately before and immediately after. So I've chosen 1.9 seconds and 2.1 seconds. That's 1/10 of a second prior and 1/10 of a second after. Now you could also do it 100th of a second prior and 100th of a second after. You can try different numbers as long as it's the same very short time increment before and after. But these are the values I've chosen. So for the time of 1.9 seconds, I get 7.144 meters per second. At a time of 2.1 seconds, I get 8.484 meters per second. I take those values, plug them into this equation. Average acceleration is change in velocity over change in time. I plug in those values and I get 6.7 meters per second squared. You might want to, for some variation, try some slightly different numbers. If you want to be less accurate, try a larger increment. Try 1.8 seconds and 2.2 seconds. If you want to be more accurate, try 1.99 seconds and 2.05 seconds. Just try different increments and see how much it varies from the answer that I got. Problem number 59 says you're driving at 50 kilometers per hour when the traffic light 40 meters away turns yellow. Find the constant acceleration required to stop at the light, and B, the stopping time. Is the acceleration reasonable? Here's the given information. Now, from the beginning, it says 50 kilometers per hour. We're going to want this in MKS units. So here I've already converted it to meters per second, 13.8 repeating meters per second. We see that it's a distance of 40 meters that we're going to have to go. And the idea is that we want to stop within that 40 meters. And ultimately, because we're stopping, the final velocity is 0. We want to know the acceleration. So given v0, delta x, and v, the equation to use is this one. Here's our kinematic equation where my pointer's at. v squared equals v naught squared plus 2a delta x. We want to solve that algebraically for a. So we get v squared minus v naught squared over 2 delta x, plug in all the values, and we get negative 2.41 meters per second squared. The negative is because we're slowing down. Now question B is asking for the stopping time. And the stopping time we're going to use, since we know v, we know v naught, we know a, let's use this equation. V minus v naught over a, and we get 5.76 seconds. And an acceleration of negative 2.41 meters per second squared, as best you may be able to judge, that's pretty reasonable. Gravity pulls you down at 9.8 meters per second squared, and it's significantly less than that. So I think it seems pretty reasonable. Number 61 says a golfer putts her golf ball straight toward the hole. The ball's initial velocity is 2.52 meters per second, and it accelerates at a rate of negative 0.65 meters per second squared. Will the ball make it to the hole 4.80 meters away? If your answer is yes, what's the ball's velocity when it reaches the hole? If your answer is no, how close does it get before stopping? All right, so it's one-dimensional. It's going straight across the ground, and it's got a negative acceleration because it's slowing down. There's my initial information. V naught is 2.52 meters per second. And we can ask the question this way. How far will it go before it stops? So when v equals 0, what is delta x? And we'll see what happens, what kind of answer we get. And there's the acceleration. So v squared equals v naught squared plus 2a delta x. We can solve that for delta x. So we're basically looking for how far will this ball go if nothing gets in its way and there's no hole that it's going to drop into. How far can this ball go given this speed and this acceleration? So we plug in these values and we get 4.885 meters. So because it only had to go 4.80 meters to get to the hole, the ball will get to the hole because it's got enough momentum to take it a bit farther. Now question B is asking, all right, recognizing it will get to the hole in 4.80 meters, how fast will it be going? So we know V naught, we know A, we know a delta X of 4.80 meters. Let's plug those into this equation and see what its speed is. When you plug those in, you should get 0.332 meters per second. Number 71 says the rock and roller coaster accelerates in a straight line from rest to 60 miles per hour in 2.8 seconds. What is its constant acceleration and how far does it travel during the first 2.8 seconds? As soon as you see 60 miles per hour, you should think we need this in MKS units, meters per second. So let's convert 60 miles per hour the way we learned in chapter 1. And there it is, and you get an initial speed. Actually, initial speed is 0 meters per second. You get a final speed of 26.816 repeating meters per second in a time of 2.8 seconds. We want to know acceleration, so given v naught and final v and t, let's use this equation that acceleration is change in velocity over time, plug in those values, and you get 9.58 meters per second squared. Let's use two significant figures, so 9.6 meters per second squared. Question B is asking how far does it go during that 2.8 seconds? So this is a good equation to use. X equals x naught, which is 0, v naught t. Well, v naught is 0, so that goes away. And all we're left with is 1/2 at squared. We just solved for a on the previous problem, so we get 38 minutes. I'm sorry, 38 meters. Number 75 is one of vertical motion. The Jurassic Park ride at Universal Studios theme park drops 25.6 meters straight down, essentially from rest. Find the time for the drop and the velocity at the bottom. So it is dropping. It is acceleration due to gravity that's pulling it down. So you see the picture that I've drawn at the top. y naught equals 0, v naught equals 0. It's from rest. I'm making down be the positive y direction, so acceleration is positive 9.80 meters per second squared. And it will go a distance of 25.6 meters. So at the end, y equals 25.6 meters. We want to know v and t when it reaches the bottom. So an appropriate equation is this one where my pointer is at. V squared equals v naught squared plus 2a delta y. We know all those values. You can see them in the picture or around my pictures, so plug them in. V equals square root of 2 times 9.80 times 25.6. And we get 22.4 meters per second. That's its speed when it gets to the bottom. For time, let's use the kinematic equation that involves velocity, acceleration, and time. I solve it for time, and I get v minus v naught over a. So 22.4 minus 0 over 9.8, and that's 2.29 seconds. Question number 79. The first astronaut to reach Mars decides to measure the gravitational acceleration by dropping a rock from a 45.2 meter high cliff. If the rock falls for 5.01 seconds, what is g on Mars? So it's a similar setup to the previous problem, number 75, although this time we don't know what acceleration is. That's what we want to solve. So we know y naught and v naught are 0. It's going to drop down a height of 45.2 meters. It's going to take a time of 5.01 seconds, and acceleration is what we want to solve for. So we're going to use the equation, the kinematic equation that uses those values. Let's go with this one. Y equals y naught, which is 0, plus v naught t, which is 0, plus 1/2 at squared. We then solve for acceleration, 2y divided by t squared. And when we plug in the y of 45.2 meters, we plug in the t, 5.01 seconds, and we square it. We get 3.60 meters per second squared. So that is acceleration due to gravity on Mars. Number 95 says, you throw a baseball straight up at 12.1 meters per second. Find the time when the ball is 5.20 meters above its launch point. Find the velocity at each time you found in part A. You look at my picture, I have it going up and then going down, and it's going to pass this point, this height of 5.20 meters twice, once going up and once going down. We want to find both of those times. So I've written the given information around the picture. V naught is 12.1 meters per second. Y naught, the height from which it's launched, we're just going to call that 0. And we're interested in y equals 5.20 meters above that launch point. I'm making up the positive y direction, which means acceleration due to gravity is negative because it's down 9.80 meters per second squared. So I'm going to find the kinematic equation that involves time plus the given information. We're going to need this one, y equals y naught plus v naught t plus 1/2 at squared. Plug in the given values. Y naught is 0, and the other terms are non-zero. In order to solve this, we recognize it's a quadratic equation. We need to use the quadratic formula or a graphing calculator. So I will put it in standard form. This is the form you need to use the quadratic formula. So 4.9 t squared minus 12.1 t plus 5.20 equals 0. And whether you use the quadratic formula or a graphing calculator, you should get these two solutions for t, 0.553 seconds, and that's the time when it's going up. And then a bit later, 1.915 seconds, that's the time when it's coming back down. Now, part B asks for the velocity. And so let's do the first time, 0.553 seconds. We're going to use the equation v equals v naught plus at. We plug those values in, and we get plus 6.7 meters per second. Plus means it's going up. For the second time, 1.915 seconds, plug that into v equals v naught plus at, and we get negative 6.7 meters per second. So there's a symmetry there. It's going at for a given height, in this case 5.20 meters, it's going up and down, they're at the same speed, just opposite directions. And that is the end of the Chapter 2 homework. Have a great day.